Welcome back to the Deep Dive. Today we're tackling a subject that affects so many lives and has been, well, let's be honest, a source of real frustration in medicine for a long time. Alzheimer's disease.
Mm-hmm.
For decades, it felt like researchers were pouring everything into, what seemed like the obvious target.
Right.
But if you followed the news on clinical trials, you know the feeling. Billions spent, so much work, and the results, modest at best. It's like trying to fix this super complex engine by just polishing one rusty part you can see easily.
Yeah.
And maybe, just maybe, we were polishing the wrong part entirely.
That analogy really hits home, I think. It captures the mood. For nearly 40 years, let's call it the traditional view, was really locked on Alzheimer's being primarily about neurodegeneration.
Brain cells dying off.
Exactly. And the main villain, the absolute bad guy in the story, this sticky protein called beta-amyloid. The logic seemed solid. Clear out the amyloid, cure the disease. Simple.
But it wasn't simple, was it? Drug after drug designed just to clear amyloid. They largely failed.
Yeah.
And that forces you to ask some really hard questions.
You absolutely have to. If getting rid of the physical plaques doesn't really stop the cognitive decline in a major way, you have to question the whole foundation. Yeah. And that doubt, that questioning, it's created the space for a really different idea, a potentially revolutionary one, which is what we're diving into today.
Okay.
We've been looking at some fascinating material, excerpts from Alzheimer's Redefined, the Neuroimmune Imbalance Theory, put together by the Hale Institute. And they detail this huge shift in thinking.
And this shift is spearheaded by researchers like Dr. Donald Weaver and his team at the Krembil Brain Institute up in Canada. Their idea doesn't just tweak the old model, it flips the script.
Completely.
Yeah.
So our mission today is to really explore this new way of looking at it.
Yeah.
The possibility that Alzheimer's doesn't start with cells just wearing out. Instead, it might begin with the brain's own very specialized immune system going wrong, misfiring.
An immune system problem. Like an autoimmune disease, but in the brain.
That's the core of it, yeah. An autoimmune response, essentially.
Okay, let's unpack this. Mm-hmm. Because every diagram I've ever seen of Alzheimer's points to beta-amyloid and says, toxic waste. Bad stuff. Get rid of it.
Mm-hmm.
Now, Dr. Weaver's suggesting something, well, radical.
It really is. The shocking twist in this new hypothesis is that beta-amyloid might not be just harmful junk at all. It might actually be an active part of the brain's immune defense.
An active part? How?
Think of it like a rapid response sticky trap. Its job might be to grab onto and neutralize threats, maybe invading bacteria, viruses, or even certain toxins.
Yeah, so the amyloid is like a shield, not the sword that kills the cells. That changes everything. But if it's meant to protect, how does it end up causing so much damage? That seems backward.
That's the crucial point. That's the misfire part. And this is really the heart of the immune imbalance theory. The source material points to this critical vulnerability. It turns out that our own neurons and certain foreign invaders, like specific bacteria, they actually share some chemical features on their outer membranes.
Wait, shared chemical features. What does that mean exactly? Like a similar sugar molecule or a protein structure that looks the same to the immune system?
And precisely. Think of it like the immune system is on the lookout for a specific tag, maybe a protein pattern, that signals danger, right, on an invader.
Got it.
But unfortunately, just through how things evolved chemically, some of those danger tags look really similar structurally to components found on our own healthy brain cells, our neurons. Yeah. So this similarity, it kind of acts like a false ID. The immune system gets confused. It starts to mistake the brain's own cells for microbes it needs to fight off.
So the brain starts making this amyloid stuff, this sticky trap, to try and wall off its own neurons because it thinks it's fighting an infection, maybe one that isn't even there anymore.
That seems to be the idea. And the result isn't just a quick cleanup. It becomes this chronic, self-sustaining inflammation, like a constant low-level civil war inside the brain, an autoimmune battle.
Wow.
And it's this relentless, misplaced defense that slowly damages the neurons, leading to the memory loss and the cognitive decline we see in Alzheimer's.
Okay, that suddenly makes sense of why those old drugs failed. They were trying to remove the shield, the amyloid, when the real problem was the immune system constantly yelling, attack, at the wrong target.
That's the critical shift in perspective. They might have been treating a symptom, or maybe even a consequence, not the root cause, this fundamental mix-up in the immune system.
So we need to stop thinking degeneration first and start thinking inflammation or autoimmune.
Exactly. It reframes it as a potentially treatable condition, not just an inevitable decline.
All right, if it's about inflammation, we need to know who the players are. This specialized defense network in the brain. What does it actually consist of?
Well, the brain's immune system, the neuroimmune system, it's different from the one in the rest of your body. It's highly specialized, very tightly controlled because, the brain is incredibly sensitive.
Can't just have immune cells rampaging around in there.
Definitely not. So the main defenders, the sort of resident immune cells, are called microglia.
Microglia, okay.
Think of them as the brain's dedicated security guards and the cleanup crew. Their normal day job is vital. Clearing out debris, getting rid of damaged connections, protecting the neurons.
But in this new theory, they become the problem.
Well,
security guards go bad.
That's the idea. When they constantly sense this threat, the neurons they're misidentifying, they switch from protective mode to attack mode. They become overactive.
And start causing damage themselves.
Yes, they start pumping out these powerful, damaging, inflammatory chemicals. They go from protectors to, unintentionally, agents of destruction.
Yeah.
Trying to save the village by burning it down, in a way.
And they're not alone in there, are they? Do they have backup?
They do. Another key cell type is the astrocyte. These are also glial cells, not neurons, and they have many jobs. They help support the neurons, maintain the blood-brain barrier. That's super important. It's like the brain's firewall.
Right.
And crucially, astrocytes are also involved in modulating inflammation. They try to keep things in balance, try to calm things down.
But they get overwhelmed.
It seems so. When the microglia are constantly sending out these danger signals, even the astrocytes, which are trying to regulate, can get pulled into this runaway feedback loop of inflammation. The whole system gets stuck in on mode.
Okay, so you have confused microglia driving inflammation and astrocytes unable to stop it. That really sets the stage for this next piece, because this isn't just about Dr. Weaver's theory in isolation, is it? There was this other huge discovery.
Exactly. Here's where it gets really interesting.
We're talking about the 2025 Nobel Prize in physiology or medicine. It wasn't for Alzheimer's, specifically.
No, but it recognized a fundamental discovery about how the immune system works, one that has massive implications for diseases involving chronic immune misregulation, like this potential view of Alzheimer's.
So what did they find? What was the big Nobel-winning discovery?
They essentially characterized a whole new lineage of immune cells. Some people are calling them a third type of immune cell. Let's maybe call them immune sentinels for our chat today.
Immune sentinels. Okay. What's special about them?
They basically blur the lines between our two classic types of immunity. You have the innate immunity, that's the fast, general first response. Think of it as the blunt instrument.
Right, the immediate reaction.
And then you have the adaptive immunity, that's the slower, highly specific, targeted response that learns and remembers. That's what vaccines train, creating memory T cells and B cells.
Okay, innate and adaptive. Where do these sentinels fit?
They're like a hybrid. They have the speed, the fast reaction time of the innate system. But, and this is the critical part, they also seem to have the ability to remember past threats, much like the adaptive system.
So they react fast, and they hold a grudge. They remember the enemy.
That's a great way to put it. They retain immunological memory. And here's the kicker, why this is so relevant to the Alzheimer's theory.
Yeah.
Early evidence is suggesting that these hybrid sentinel cells are actually present, possibly in significant numbers, either inside the brain or very close to it, near the central nervous system.
So if Alzheimer's is this chronic, mistaken immune attack,
these immune sentinels could be the missing piece. They could be the component that keeps the fire burning.
Okay, let me see if I get this. Maybe some initial trigger happens, an infection, a toxin, whatever, the microglia react, maybe makes amyloid as that shield. But then these sentinels, because they remember that initial trigger, they keep telling the system, threat. Long after the original danger is gone. They keep restarting the inflammation cycle.
That's the hypothesis. That memory function could turn what should have been a temporary defensive reaction into this chronic self-destructive loop. The convergence here, Weaver's neuroimmune model, and this Nobel discovery about these memory-capable rapid responders, it's potentially huge.
It really reframes the whole goal for treatment, doesn't it?
Absolutely. It shifts everything.
So the big takeaway, the profound implication here, is that the focus isn't just about scraping away amyloid anymore. That might be like trying to remove smoke without putting out the fire.
Exactly.
The real goal now becomes rebalancing the brain's immune system. getting it back on track.
The whole therapeutic roadmap changes. We move away from just focusing on, say, neurochemistry and dive deep into immunology within the brain. We stop thinking about bulldozers for plaque and start thinking about fine-tuning instruments for the immune response.
And the sources we looked at mentioned specific directions for future therapies based on this. What's the first one?
Okay, the first major direction is about dealing with those overactive microglia. It involves developing drugs that can specifically modulate microglial activity.
Modulate, not just shut them down.
Right, that's the tricky part. You can't just suppress them completely because they still have important jobs to do cleaning up actual waste pruning connections. So we need therapies that can somehow calm down their excessive inflammatory signaling without stopping their essential functions. Precision work.
Like turning down the volume on their alarm system, not switching it off entirely.
Exactly. Recognizing the difference between a real threat and, the furniture.
Okay, and the second approach, that one sounded really interesting because it connects Alzheimer's to diseases we already have treatments for.
Yes, this one's exciting because it offers potential shortcuts. If Alzheimer's really is, at its core, an autoimmune disorder of the brain, then we can maybe learn from decades of work treating other autoimmune diseases.
Like arthritis or lupus.
Precisely. Scientists are looking very seriously at immune-calming therapies that are inspired by or even adapted from treatments used for conditions like lupus or rheumatoid arthritis, RA.
Wow. So drugs that calm down an immune system attacking joints might actually work for the brain.
The underlying mechanisms of chronic inflammation, the signaling molecules, the cytokines, they share similarities across the body. The big challenge is often getting those drugs across the blood-brain barrier effectively. But if we can adapt existing immunomodulators, treatments already used in rheumatology, for example, to work safely in the brain.
That could save years of development time.
Potentially, yes. It leverages a huge amount of existing knowledge.
And the third direction, this one sounded almost like science fiction retraining the immune system itself.
Yeah, this is perhaps the most sophisticated approach. It involves designing things like vaccines or highly specific precision antibodies. The goal here is to essentially re-educate the confused immune cells.
Teach them the difference between bad guy and good guy again.
Essentially, yes. Especially targeting those memory-holding immune sentinels, perhaps. Trying to teach the system to reliably distinguish between the chemical signature of a real threat, like a bacterium, and the similar-looking signature on a healthy neuron, fixing the case of mistaken identity at the source.
This is a genuinely different way of looking at Alzheimer's. Not as this hopeless, inevitable decay, but as a treatable immune problem, a miscommunication. That feels like a real reason for optimism, grounded in biology, not just wishful thinking.
It absolutely is. But, it's important to reiterate, we're still in the relatively early stages of proving all this definitively. The evidence is compelling, it's building, but it's not absolutely conclusive yet.
Sure.
But the research focus has clearly shifted. The goal now is really learning to speak the immune system's language well enough to guide it back towards balance.
So wrapping this up, what does this all mean? We started talking about the frustration, the failures of the amyloid-only approach. Now we've explored this massive shift, thinking about immune imbalance, bolstered by Weaver's theory and that 2025 Nobel finding. Where does that leave us?
Well, it pushes the fundamental question further back, doesn't it? If the problem is the immune system getting confused by these shared chemical features between neurons and invaders,
Right.
the really deep question becomes, what was the initial trigger?
Right. What kicked off that first immune reaction that then got stuck in that chronic loop?
Exactly. Was it a specific virus, a particular environmental toxin, maybe a combination of factors?
And that leads us to a really provocative final thought for you, the listener, to consider. If Alzheimer's starts as this defensive reaction to some initial spark, maybe a lingering infection the body couldn't clear, or exposure to something specific in the environment, then figuring out what that first trigger is could be the ultimate key. Because if you can identify and avoid or neutralize the trigger, maybe Alzheimer's isn't just treatable with immune therapies. Maybe, just maybe, it could become preventable.
Moving from treatment to primary prevention, that's the ultimate hope, isn't it?
It really is. Thanks for diving deep with us today.
My pleasure.
We'll talk soon.